Hi, guys. Welcome to lecture number 9. Today, we're going to talk a little bit about cognitive modeling, which is an older topic, and how that relates to agents in LLMs. And then we're going to talk. Then we're going to kind of make a break. We're going to basically try to look at very practical business problems where Gen AI can apply. So I'll be saying a lot about setting kind of the context for that. What business do I mean? So when I say real business, what do I mean by that? So that'll be the second part. So yes, the outline is that we're going to talk about integrating generative AI with classical AI or cognitive modeling. So what we want to do is, many of you guys might have seen this before, but there's this notion or this idea of a production system. So we want to review that quickly. And then we want to talk about this long running project, SOAR, which is kind of represents using these production systems for cognitive modeling. And then what we want to cover then is now we're going to get into LLMs. We want to cover this highly influential paper that came out in 2024. COALA, so cognitive architecture for language agents. So this is where we take this kind of more old-fashioned stuff from, there's this, I'm not sure people have seen this, GOFAI, good old-fashioned AI. We're going to take one of these good old-fashioned AI results, and then it gets brought into the LLM era. And this was a highly influential paper. So this has influenced a lot of the agent architectures, including Claude. Okay, so that we're going to cover that. That's the first part of the lecture today. And then we're going to go over these I just arbitrarily picked 9 of them. So I want to have some very specific problems for business that LLMs or agents or reasoning models have a good chance to help with. So we're going to cover that. So production systems. All right. So what is a production system? Okay. So this is kind of like when you hear about rule-based systems, these are essentially these are kind of production systems. There were a lot of variations back in the day of different engines that would use these, but like Ops 5 was one of them. Clips was another. I used Clips quite a bit at one point, but these are forward chainers. So the rule-based modeling represent the knowledge. So you have a representation of the knowledge, and then the rules drive or work around that knowledge. So what we have is a production rule which has a left-hand side and a right-hand side, and this is a very procedural kind of semantics. So what it does is basically we have this working memory, and we have a rule or a set of rules. And when the rules, when the left-hand side of the rule, the conditions on the left-hand side of the rule match the working memory, then that rule can fire. Okay, that rule then has license to fire. And when it fires, if it's selected, and we'll come to that in a second, then it will modify memory with what's on the right-hand side. And so in traditional planning, a lot of times these facts are called fluents because they can kind of go back and forth. So they're facts that are not fixed over all time. There's a kind of a time dimension on the fact. There was a lot, there's a ton of work that one could talk about when it comes to how that gets dealt with semantically. And you have this the Yale shooting problem was a classic problem with trying to get logics to do this kind of in a deeply semantic way. So anyways, there was the frame problem for planning. But so there's a lot of depth here in terms of kind of how these were dealt with. But what we look at here is we're going to look at this, the idea of doing it the following way. We have working memory, which is the store of facts describing some type of state space, some type of state, and also might be embedding kind of what problem we're trying to solve. So that kind of gets implicitly embedded in the state space. And then in these classic production systems, we're a bit more practical minded, so we're not going to worry about kind of like a frame problem or Yale shooting problem type issues. And so what we go through this recognize, act cycle. So the loop is basically we match the rules against the working memory. Then we resolve conflicts because we're only going to fire one winning rule. So we have to have a way to prioritize the different rules that do match, and then fire maybe like the most specific one, or have some other kind of controls in there that decide which one fires. And then we're going to update working memory, and then we're going to repeat that until the goal is reached, or until we reach a point of quiescence where we can't, no longer, there's no longer any rules matching. And there's maybe a special end state that we can talk a little bit about that. So what can happen wrong here? One of the things that can happen wrong or cause difficulty is that no rules match, or multiple rules match, and you have to resolve them. So that's an impasse. And what's really interesting about these architectures is what they can do, or what SOAR does at least, and we'll talk about SOAR in a second. What it will do is it will take that, and then it will say, okay, well, that's our new goal. Our new goal is to resolve that impasse. And then it will bring that down to a sub-state space, and then we'll be doing it over that state space. So this whole idea of how when we do problem solving, or when we do actions or planning in the world, how we tend to regress on the problem and go down to solve sub problems, that gets explained in this, or that gets modeled in SOAR. Well, we'll see. Okay, but still going back to just the basic production systems. Production systems relate to, if you go way back, they relate to post-production systems. So this is kind of in the dawn of kind of theoretical computer science. And then also they relate to Chomsky's hierarchies. They are actually a type 0 grammar in Chomsky's hierarchy. So it's a production rule where, so in Chomsky's setup, it's basically you have terminals, non-terminals, and you have rules. And you can basically have arbitrary rules, arbitrary sets of terminals and non-terminals. When they match, then you could have an arbitrary an arbitrary string of terminals and non-terminals. And that's Turing complete. So that's a full computational machine. Okay, so they have that. So these are again this idea of doing forward chaining. I think the cognitive scientists do say that most human reasoning is forward chaining. I mean, logic, you have modus ponens, modus tollens. Most people use the modus ponens, so they're going forward. Now, okay, let's just kind of like show some examples of computation. So above here, what we see here is and this is from the paper, the COALA paper, we have divide by 5. Okay, so what is this doing? So these are the rules here. Now, this rule here that has the bullet above it, that means that's a final rule. That's the final one you're going to apply. And then this is the ranking. So this is the hierarchy. If you can apply this one, always apply this one, until if you can apply this one, then apply this one. So in other words, when you apply this one, means that you can't apply this one up here. And then this right here is just a special case here for the empty string coming in. But anyways, here's working memory. So working memory starts out with star and then 11, I believe it's 11. Yes, 11 units, slashes. And then what it does here, it's going to divide that by 5. So the first thing it does is it will take 1, 2, 3, 4, the first 5 of these, it'll match that, and then it will put a forward slash, and then so it'll move for each 5 of these, it'll move a forward slash to the left-hand side. So this is what gets, if you look at the way this rule definitely applies here to this. And what you see here is that it actually moves it over. And now we have 6 of these right here. And then this rule can apply again, and it'll move over yet another one of these. So that's basically going to be 5 goes into 11 twice with a remainder of 1. Okay? And then this rule no longer can apply, but this one can apply. So it can just consume on the final pass. It just basically goes in here, it consumes, or doesn't consume it, but it just processes it through. And it basically just leaves them the result. And the result is then finished. Okay, so the bullet here means that it's going to be the final step. Okay, so you can put it in any arbitrary. You could put in 1,000 stretches here, and then it will divide that 1,000 stretches by 5, and whatever well, there won't be a remainder in the case of 1,000. But it will have then 1,000 divided by 5 strikes left of the star symbol. Okay, so it works. You could also envision it a thermostat. So if you can, the working memory can have access to sensors. So the sensors kind of move in what the reading of the thermometer is. And you have also actuators, so you can actually turn on the furnace, turn off the furnace. You can make a call for repairs or turn on the electric heater. What this right here will do is this basically, if you in any state, this will bring you, well, if it's too cold, and this is in Fahrenheit here, so if it's freezing, what it will do is it will turn on the electric heater and it will call for repairs. Okay. And then you can actually start looking. There's actually kind of a fair bit of dynamics in here of potentialities. But the point here is that what we have here is we have, once we get into the right temperature band, then we stop. We turn off. We're done. We've set the temperature to the right amount. Okay. So anyways, but this just shows kind of it being applied in like a little real world thing. Right. Now let's talk about SOAR in particular. So SOAR is this cognitive architecture that's based on production systems. It used to be based on this acronym, but they say that should no longer apply. It was created by John Laird, Newell, and Paul Rosenblum in 1983. So this is coming out of Carnegie Mellon. So that was one of like the main centers of AI research, or is one of the main centers of AI research in the United States. And then it was further on, it was developed by Laird's group at the University of Michigan ever since. Okay. Now I had nothing to do with it and all that, but I will say one thing is that when I was a wee one, my first AI course was Laird and Durfee. They taught this, and we of course covered production systems in that course, and it meant as many other things. But I was hooked. I was gonna AI was I was gonna do work. So Laird and Durfee were inspiring. So I because I graduated from University of Michigan, so I had some experience of watching these guys in action, and they're very good. So. Yeah. So, but it went on. It basically, the point behind it was supposed to kind of, it aims to be a unified theory of cognition, with one fixed architecture capable of the full range of intelligent behavior. So it's very ambitious, and it's using search as kind of a unifying kind of theme or unifying mechanism. So, so search is very general. So it's like it has to do with like state space, and you can have operators that change state space, and then you can always check state space to see if you're getting closer to a goal. So if you guys had like a beginning AI course, like all the search stuff is like iterative deepening and all these other kind of techniques in search can apply here. But actually, the thing is that it's mostly just forward training in the case of SOAR. Which again, they're trying to do cognitive modeling. They're trying to kind of get something that's kind of like, seems to kind of be tracking with how humans solve problems symbolically. So this is symbolic AI. All right. So the decision cycle is basically what you do is you have the state. Then what you do is you propose a set of rules because these are the ones that match the state. And then what you do is when you find those ones that you go through this proposal phase, and what that does, it kind of sets up a set of different operators that could be selected, and then you select one of them, and then you apply that operator. Okay, you actually apply that, and when you apply the operator, you then change the working memory. The actual fluents in the working memory get changed when you apply that. And then you add that result to it gets changed in working memory, and then you repeat. So you kind of just do this in a forward chain. So this is kind of this shows us a little bit why it's a bit more based on cognitive architecture. This is kind of this is a very, very coherent way of looking at the whole problem. It has really all the ingredients that we need here. So okay, so we have the idea of memories. So we have the symbolic working memory. This is that scratch pad, if you will, where we're applying the rules and we're changing stuff and we're adding stuff back into working memory. So this is kind of what you hold when you kind of are going to like, I mean, your working memory gets, when you have to kind of go and get yourself a cheeseburger or a hamburger or whatever, you're sitting there, you decide, I'm hungry, I need to get a hamburger. And then you're going to go down the stairs, you're going to go across. So, if you're at work and there's the hamburger place that is a couple buildings over. You're going to be kind of like navigating that and but you're not going to think about it that much because it's so automatic at this point. But you're just going to be working up your working memory to kind of remember, well, I'm on the stairs now. I'm kind of going up the stairs or whatever, down the stairs. Now I have to reach in my wallet. Okay, I'm going to pull out and pay for the burger, etc. Okay, but that kind of just goes away, right? That's just kind of, it's very transient. This symbolic working memory as you go through things. Now, long-term memory is similar. So it's a memory. So it's kind of it's being recorded. we have basically three classes here. We have procedural memory, which is how to do stuff. Okay, this is kind of like what are the steps you take to get things done. So these are the actual rules. So the actual rules here that are going to be applying in working memory. So these operators rather. Operators and rules are a little different in SOAR, but basically those kind of come in. So that we have this whole stash of these background operators that maybe in certain circumstances you go and then you'll actually retrieve those and bring those into working memory. Okay, so they can apply. Then we have semantic memory. So semantic memory is interesting. Semantic memory is kind of like just the things and kind of like the ontology, if you will, of what is. And in fact, the ontology work relates to a lot to this. So it's kind of what are the definitions of the things, in the world. So so there's a huge history here, but like Psych is trying to kind of build up the giant ontology, et cetera. So this is the idea of semantic memory. And then this is kind of a critical one. That is episodic memory. So this is the idea that you actually remember the specifics of earlier events. So you remember the time that you and your sister visited your grandmother and the stove broke or something, right? That time in childhood, right? Or so it's your own life history, right? So you have access to all those memories. Those are long-term memories, and those can be recalled and brought back. Can be brought into working memory as well. Okay, so it has memory, and then what do we talk about? So episodic learning is almost automatic. It's almost just like kind of like logging what goes on as you experience things. Semantic learning is tricky because that has to do with like you can have like learning processes in here where you actually then find out or you kind of propose or discover a new concept and you add that to your semantic store. Then you have what's called chunking, which is really powerful, and that has to do with when you realize that let's say that you really struggled with something and you went through some kind of recursive descent and you kind of spawned a subspace where you were doing the work over that. You finally got it to work, right? So you have this record of going down into a subproblem and working very hard to kind of get that to work. And then once you've done that and you've achieved the goal, then what you do is you compile that into a single rule that works at the original space level. So this is that idea of like I think there's a quote by Alfred Whitehead that says something like civilization proceeds by how many things we can do without thinking about them. So a lot of very basic, like when you string things together, you string together a whole bunch of actions, and then you discover, okay, well, that action achieves a higher level goal. I'm just going to compile that whole string of things together into one general rule that can apply. So if you guys, anybody's learned Rubik's Cube, that's how Rubik's Cube works, right? If you start just doing the operations, what you'll notice is there's a set of combinations. What they'll do is they'll move some of the subcubes or some of the surfaces will move in an exact pattern, and the other ones will stay constant. So it's an invariant. So those are called macro operations, and those are the result of chunking. So when a person does Rubik's Cube, what they're thinking is of terms of, I'll do this combination, and I know what that will achieve. But each of the individual ones is kind of going off on in a strange trajectory. But once you kind of bring them together and you compile them into a macro operation, then you can solve Rubik's Cube. Okay, that's kind of that's how you do it. So that has to do with chunking. So it's kind of a complex process of compiling the rules back into procedural memory. Then we have the whole decision-making process where you have which is what I covered earlier, this proposal, this action selection, and then the application. That's represented over here. All right, so, and then what you have here also is you have buffers that are coming in from perception and motor. So really this architecture really is all-encompassing. It really is, it's a quite powerful architecture. We'll see that it even improves much better for the LLM world. So, okay, so some additional features. I already talked about this a little bit. We have this idea of impasses and subgoaling, chunking. Yeah, so that's I think the Rubik's Cube thing. So another thing just to keep in mind that I know I talked about it a little bit. I talked about what is machine learning? And then the current way people talk about machine learning, they talk about We've got supervised, unsupervised, and reinforcement learning. And then I think I'd mentioned it. I said, oh, there's this thing called EBL, explanation-based learning, which is a separate species. It's very much a separate species. So it's like the example of explanation-based learning is the following. There's it's a kind of like, all right, the simple example is like, why does a child only touch the hot stove one time? Okay, you don't have to train them and do stochastic gradient descent. They use the knowledge of that and they compile it into a rule that says, do not touch the red hot stove. Okay, that's an explanation-based learning. But I think the example I would just mention here, which I think is kind of very vivid, is this example where they had this little cartoon where they showed all these cavemen sitting around, and there was a fire. They were sitting around the fire, and each caveman was holding his meat with his hands over the fire, but singeing his hands in the process. Okay, so that's the first thing. You see all these cavemen that are it's kind of idiotic in a way. They're just using their hands to kind of hold the meat over the fire to cook it. Then you see one caveman who has glasses on, and he takes a stick and he puts that meat at the end of the stick and holds it over the fire. All right. So he's cooking. So he's not going to burn his hands, but he's going to cook his meat. Right. And then on the next step, you see that all the cavemen, once they saw that one time they saw that that caveman do that, and then now they're all doing it. So they've all kind of created behavior in a one shot experience. So they were able to kind of adopt new behaviors. Okay, so that's something that we don't really talk. I mean, that's something that we haven't really. How do you do that with supervised, unsupervised, and reinforcement learning? It's not. Those aren't really equipped for that. This has to do with explanation-based learning, where you're using knowledge and learning to do this chunking to kind of to figure it out and then to save it off as a rule. Okay, so it encompasses EBL. So that's really pretty important. All right, so but modern SOAR also adds in reinforcement learning plus. Okay, so yeah, it went on, but I think the thing is, I think what's nice about, or what's interesting about, what's interesting about SOAR is that when you actually watch the traces of SOAR and how it actually handles problems, and then you think introspectively about how you do it because we're all kind of talking. At least I am. I'm always talking to myself. I mean, there's some kind of stream of consciousness, some kind of set of things I'm saying to myself, or I'm kind of representing to solve problems in my daily life. And it seems like it kind of corresponds to what SOAR does. So that's kind of it's kind of a powerful system in that way. Now that's all like this work has been going on forever. So this is all predates the LLM era that we're in. This paper came out though in 2024, and it basically is going to kind of re-explore this stuff. And the first thing it does, okay. So I was talking about how SOAR is really good about like, yeah, once you have all the rules in place and you trace them out, it's kind of like, wow, that actually makes sense. That's kind of how it seems kind of corresponding to introspectively to how we think. The thing is, though, is that there's just so many rules. It's very hard to specify them. So the world is very complex, and we have just too many rules that we have to kind of craft into something like SOAR. And then also the rules are fragile. I mean, the world is stochastic, so it's kind of it can be brittle. So anyways, so those are like some of the major limitations. Interestingly, that if we look at it the following way, we can get a lot of rules if we look at this production system reasoning as what LLMs do. So if you look at it in this way, that if X is the prompt to an LLM and Y is the completion, this actually defines a production rule: X goes to X, Y. All right. And this right here, these kind of sequences here kind of show you, like, here's a zero shot. You just put in a Q, and then the LLM is going to it's going to pick one completion. So it's in some sense, it's kind of sampling from all these probabilistic. I mean, there's like probability we'll do this one, that one, but let's say the temperature is at 0 or approaching 0. So it's deterministic. I mean, it will give you the same completion every time. That's just a production rule if Q goes to QA, right? Because it's doing its inference over this working. So this is what, if I put this into working memory, the queue, and I let an LLM fire on it, then it's going to put in, then working memory will now contain Q and A, right? So it's kind of additive. If I have some extra mechanism that does this, I can also do few shots. So I have Q here, then maybe just as a deterministic problem, I said, oh, here's Q. Okay, I'll set up a set of QA, 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 and then Q, and then I'll let the LLM then generate that same thing again with A at the very end. So this is exactly the few shot example here, kind of put it into production rule syntax, all right? Same with RAG, and then these Socratic models where you're just kind of like hopping along. You say, question goes in, then we have observations, then we take the result of that and put it again through another chain. Then finally get an answer out. Self-critique. So we have the idea of critique models as well. So you can pretty much frame all these things as productions, in LLM-based productions. So that's kind of a good insight here. So here's now SOAR, the architecture of SOAR reworked into these language agents. And so this is quite interesting. Let's just go over this kind of quickly here, just so we can see kind of how this works. All right. So we have procedural memory, which can be, in this case, it can also be like agent code. It can be like it can be actual like I mean, we'll see this in I'll come back to this agent code. Semantic memory. Right. I mean, this again, this winds up usually just being kind of content that's kind of plopped out, or kind of prompt material that's plopped out of the LLM. Episodic memory, likewise, is kind of the log of the LLM and other things. So, what's interesting here, though, is that we have we have memory. So we have long-term memory. These are long-term memories, which basically mean that they're being kind of spit out to the file system, or put into a database or something. The LLM, it's a little bit funny because it hasn't really been quite worked out. What is the status of LLM? What's the status of fine tuning? So you could actually envision kind of bringing fine tuning into this, or even setting up full LLM runs where you're building an LLM. You could potentially bring that in, but it's kind of a little bit, this is an architectural framework. There's like spaces in there to do that, but it's not that well defined. But semantic memory and episodic memory, those can wind up just being material that's kind of got spit out of the LLM, or prompt material that was kind of initial to the problem. So this is what's interesting here. So we have what's called an action space. So when we talk about when we apply the next production, or we apply the next thing, what are we actually doing? And this is quite interesting. So what we have here is we have reasoning. So what reasoning is in this case is if we've loaded stuff. So, by the way, this working memory here, what is that? That's your context window, right? This is the or your context, which is what you're going to be placing into the context window. So working memory is very much just kind of like, what are you, like, what's the next, this thing that you're managing that you're going to put back into the LLM on the next iteration. And of course that context can wind up having retrieval. Like we can wind up retrieving like some episode from our grandmother, visiting our grandmother. We can retrieve that, and that can then become part of the context that then gets put into the LLM. So it's very general. So, but let's look and see what we have here. Reasoning is simply taking what's in working memory and iterating on that. That's what reasoning is. Okay, and this can go in cycles, right? We can have we can do several cycles of that. Now, retrieval is going out to one of the long-term memories and then bringing material in to make that part of the context for the next iteration. That's retrieval. And together, so every time you do an action, it's going to be one of these. It's going to be one. This is what the result is going to be. It's going to be basically, are you going to do more reasoning, or are you going to do a retrieval that is bring something new into the context? Or are you going to do learning, where you're going to be putting something back? You're going to be putting something into the long-term memory. So these are the kind of so these are all like internal kind of cognitive states, or internal cognitive actions, rather. It's not states, internal cognitive actions that you're performing. And what's really nice is it just kind of like really just like it encompasses like some of these really fundamental concepts and says, oh, those are internal things. Planning then is a notion of doing retrieval and reasoning and retrieval, reasoning and retrieval. That's the notion behind planning. And then external actions, when you actually do something, externally, what that winds up being what's called grounding. So you're actually going in, the agent is grounding its actions in the environment in which it's actually situated. So another thing also just to keep in mind here is that observations can be streaming in the whole time. And observations basically just they go through maybe specific processors and they wind up being in working memory. There's an interesting thing here that there is some work. I was looking into doing it for recitation, but I don't think I'm going to. But it had to do with like going from scenes, so we can actually see like picture scenes, and then turning those into kind of like language descriptions of the scenes, and that would then keep this to be a language agent because we would then dump the language into the working memory. So it's pretty interesting. Okay, so those are the action spaces. So when I say, oh, the system's planning, what does that mean? Oh, it means it's doing retrieval from the long-term memory, bringing that into working memory, and it's then doing reasoning over that. That's what it is. That's what the definition of planning is. So it's nice that it has this, and also that we have internal actions. Most of the actions actually are internal. If you think about it. Okay, and then the decision making here is just simply this: is that what we do is we get an observation. Then we do this planning, right? So we do this this loop here. Then we evaluate. We're going to evaluate. This is very much back to this idea of proposal, then evaluate, and then apply. So when we select it, that determines which one we're going to actually use to change working memory. Okay, and then execution, the actual, engaging the actual effectors to actually get something done. Okay, yeah. So the papers in our readings, and I think it's a good kind of way to kind of organize the way to look at all this. So what they did in the paper is they went retrospectively and they essentially kind of captured this. Essentially said, well, okay, this is like there's like this robot chef, there's this web search, React, this is a Minecraft agent. So there was all these agents that did this stuff, and what they're trying to do was so one of the things that happened in cognitive modeling, which was unfortunate, was there were a lot of different groups that had like slightly different terminologies, but they were all talking about the same thing essentially. SOAR was of course one of the best ones. I mean, it was one of the best thought out ones. But there were a lot of other kind of rival ones, and they had a different language. And then the problem with that is that you get people if we can't kind of if a community can't kind of settle in on like a terminology, then a lot of times what happens, and it's very unfortunate, even though they are talking about the same things, they talk about them in different ways, and then you have drift, and then you have camps that fight over the meaning of words, and that is just not where you want to be if you can avoid it. So this is kind of like standard, like you might say, oh, when you standardize it, then isn't that kind of like reducing the creativity? I don't think so. I think there's a lot to be said for kind of trying to get standard kind of terminologies. So that's in part what this COALA paper is trying to kind of achieve is that. And so retroactively, they show that, oh yeah, they can kind of explain or describe some of this earlier work. This was pretty good earlier work that they were able to kind of do that. And then also, you never really know exactly, but it's presumably it has influenced Claude at least, and probably OpenAI as well. So the idea then is that, well, what's working memory? Okay, that's context. Procedural memory in Claude, it would be like the project rules, the instruction files, like the Claude.md. So that's part of your procedural memory. It's like those are your productions in some sense. Is those things the skills. Semantic memory, that's like if you index the code base for facts or if you have API documentation. Semantic maybe is not, there's like, I don't know, semantic memory is kind of a funny one. Episodic, though, would be like the saved shell history, the session trajectories, and the previous debugging logs, stuff like that. So, so I think that it's really useful to kind of like at least kind of get exposure to this and to kind of see things in this way. To kind of organize, because otherwise, again, it's like we're looking for the kind of the fundamental kind of building blocks to kind of think about and build agents. Okay, and so I think this COALA paper is going to be was a real kind of turning point in some sense to kind of standardize or to kind of like at least elaborate that and show give kind of a roadmap to kind of what ultimately is going to be being looked at. Okay, so that was the first part of the lecture, and then we're going to go on now to something much more practical, kind of like looking at trying to get this stuff to get this to So now we're going to go on to the second part of the lecture. Okay, guys. What we're going to do now is we're going to talk about how we're going to apply this stuff. I mean, how are we going to, solve some real problems. Okay, so if you recall from the very beginning of the course, these were the kind of like the overarching kind of questions in this using the LLMs in data management. So how can we use this technology for reliable access to private unstructured document data? Okay, right. So it's kind of like, I think the immediate answer might be RAG. How can we use the technology for reliable access to private SQL databases? Now the answer there is like, well, text SQL, the reliability is kind of an issue there. So we're kind of given some pause on that. But maybe there's some ways that we want to bring in, at least we want our SQL databases to kind of be brought into usefully and reliably brought into business operations. And then how does our notions of transactions, so this is kind of an interesting question about like, if we're going to let all these agents kind of run willy-nilly, if we have multiple agents and we're going to let them run willy-nilly over the database, what does that sound like? That sounds like transactions. And what do we know about transactions is that they should be serializable, right? So there's kind of an issue or question, maybe overarching question of agent serializability. And that's kind of an interesting question about how are we going to really do that. And so these are kind of like overarching questions, right? But these problems are too abstract to be useful. I mean, they're like kind of, well, yeah, okay, this is like 10,000 foot flyover territory. So we need to kind of get down into something more specific if we want to get something useful. Okay, so the thing is, what I want to do is like when we talk about concrete data management, I want to talk about companies that are doing stuff worth doing. So this is kind of has a more kind of enterprise, or not enterprise. I'm sorry, small business, medium-sized business, like the real businesses that are really doing stuff in the world. Not to say that big businesses aren't, or really small businesses aren't either, but it's just I want to focus on this because this is where with the tangible results. So companies that are doing stuff that is worth doing, and I'll say that a little bit more specifically, companies that implement the modern data stack. So just, I'll describe what the modern data stack is in general terms, so that that we want to stick with companies that are doing that, because otherwise it gets very difficult. And maybe I'll make some statements about that. Now, the question is, what is a problem? What is a concrete problem? Well, it has a person that's associated with it who usually like addresses that problem. It has the problem itself. What is the problem that's being dealt with? And then what is the benefit to actually solving the problem? Okay. And then maybe you would even add in some stuff about like, well, what are the risks of a poorly, what is the risk associated with errors or with failure to solve the problem? So sometimes it's not that big of a deal. Sometimes it's a huge deal. Okay. Now you have a problem, and then separate to that, this is kind of like the whole kind of problems and algorithms kind of distinction in computer science. We have an approach to the problem. So how are we actually going to do the problem? So how are we going to actually solve the problem? And we can have, of course, multiple approaches to the same problem, and those, of course, naturally should kind of compete or they trade off between themselves. Between the different approach, the different approaches trade off something, or an approach is just bad and it's being dominated by another approach. So it's an algorithm or description, an implementation, and then of course we need to have a way to evaluate the approach, an evaluation. That the evaluation can also be associated with the problem itself. So this is just kind of general talk here. Okay, so what are companies? What's the setting here? Abstractly, most companies you can kind of see them in the following way. They go through a phase of deal acquisition, so they have to drum up business, and so they can do this. They have outbound sales, marketing, inbound sales. And also, part of the deal acquisition thing is to maybe do an inspection. So, for instance, they look at your car and they say, well, they're going to do an inspection, and then they're going to give you a estimate about how much is it going to take, or there's consultations also. They generate a quote. They basically say, all right, here, I can do this for you for this. Now, some companies don't have really much in terms of inspection. They're missing these. So like a company like a restaurant, it basically does marketing, but then the idea behind, they want to get people in the door and looking at the menu, and then they're going to make their orders, etc. Now, the other part of the business, of course, is fulfillment. So in other words, people are, they want to get something out of it. They don't want just like they're not just shopping puffery. They want some real. Most of the time, I tend to think about real business about like giving real product. Something that's like a hamburger I can eat, a car I can drive, and if I have to have physical things being done is usually what I'm thinking of here, because that's what people are going to pay for. Right. So these are companies. I say companies worth doing stuff worth doing. It's like there's no great mystery what the demand is for these companies. Right. I mean, if you're selling wristwatches, people want to watch. Right. Or if you're selling, a lot of the stuff on the internet, of course, is like they're selling stuff like selling a dream. But I don't consider that really real business. I try to stay away from those kind of companies that are selling a dream, or even I think like the fire. I'm not anti-fire like that is financial. What is it? Financial, insurance, real estate. Okay, insurance. These things are useful things, but sometimes it's a little bit kind of shell game-ish on that side of things. So it's I'm thinking of physical, kind of tangible things. That's a company that most of the companies I deal with are just like, well, I'll give you my money, you give me a product, right? Okay. So these are the three functions of a business, right? There's like to get the deals, to drum up the business, then to fulfill. So this has to do with like getting supply chain management right, subcontracting, like labor, actually doing the work, inventory management, scheduling workers, etc. Then managing projects, etc. So logistics, etc. There's a whole bunch of things that are involved in the fulfillment aspect. But of course, companies like if you are really good at getting deals, but you're really bad at doing fulfillment, then you get a bad reputation, right? If you're really bad at getting deals, but you're good at fulfillment, maybe you kind of limp along. But it's hard to say. But you need to have business coming in the door. So then support is kind of all the stuff that kind of holds this together. So support for this whole kind of thing to function. You need to manage it. You need to have accounting, human resources. You need facilities management, licensure management, public relations, collections. So you need to have some function that basically makes it so that you don't want to get deals, fulfill them, and then have the customer kind of like dodge out of paying. You need to have collections. Right, and then there's like kind of like documentation around the business, all that stuff. So these are all kind of support functions, but these are not in and of themselves profit centers, right? Profit is 1 and 2. That's what keeps the company going. Okay, but without if you have like good deal acquisition and good fulfillment, but you have bad support, then maybe you're going to have lots of problems, and it could be so ideally you have all three of these kind of going well. Okay, so now let's talk about the modern day. So that's an abstract way. So that covers a lot of businesses right there. I think that maybe it covers all of them. All right. Now the modern data stack. What is that? So this is kind of. So I did a survey actually with different companies to kind of try to get an idea of how many of them were actually doing this. The majority are doing this. This is kind of the companies I contacted on LinkedIn. The majority are basically doing a best in breeds approach, but there are some that, and I'll talk about that in a second, that they've done more of a they've bought like a SAP, or they've bought like a one like they're in some ecosystem where all these kind of tools are there and already integrated. There are pros and cons to that. But for the most part, companies are kind of, because of the way things work out. I mean, most companies will actually do a best in breeds tool. So here's how it works. You have all these departments, right? So up here we have all these different departments, all these different domains, or like units of responsibility that are doing activities inside the company. Now, each of those have professionals that are working in those units, and they tend to like to use well-designed tools specific to their role. Okay, so for example, an accounting department might want to use like a tool like, there's one tool called Sage in Tax. There's a whole bunch of different accounting. There's what is it? There's the QuickBooks, right? So yeah, so Bankman Fried's company was using QuickBooks. There was a multi-billion. Anyways, nothing against QuickBooks. Production wants like maybe a Procore, that's a construction tool. Sales wants Salesforce, so they want HubSpot or something. So the CRM, that's a CRM. So the point is that now, notwithstanding all the talk about the SaaS apocalypse and where people say, oh, they're going to vibe code these things up. Even if you vibe code up a tool, that tool then, of course, you would wind up advancing that tool, and it would wind up being something that's used by the people, those professionals that are doing that function inside the company. And generally speaking, you don't want to change the tools around too much, because these people they're good at kind of navigating those tools. They get kind of good at they can see through those tools. They can it's kind of set. It's kind of built around their profession. So it's got a lot of good design in it. So I think it's kind of like, again, notwithstanding all the talk of the SaaS apocalypse, I think that a lot of these tools are hanging around. Okay, now there might be more competition now for pricing these tools, etc. But anyways, yeah. And most of these tools allow for like custom objects, properties, or workflows, so you can configure the tool around the specifics of the business, which is really important. Okay, so we have a kind of a whole set of tools that are doing different things, but the point is that you need to weave these together, right? So extract, transform, and load, ETL or ELT, either way. What you want to do is you want to actually replicate this stuff up into a central database. Okay, and that database, basically, what you do is you make REST calls on the tool interfaces, and you pull in the data and you replicate the data into this SQL database. And right, I mean, so the APIs, so all these kind of best in breed tools, they all have APIs, because if they didn't, the market would reject them. I mean, everybody knows it's our data we're putting in there. We need a programmatic way to pull it out. Any SaaS tool who tries to play tricky around this, good luck. I mean, your customers are going to hate you if you're trying to kind of sequester data in there so that you're not, because they're paranoid about you migrating to some other platform. If you do that, you are asking for serious trouble. If you are a vendor of a SaaS tool, good luck. Okay, so they all allow for access into the data. So you can periodically pull the data from the tools into a central SQL database. So this is not. There's a lot of aspects to this to try to get this as fresh as possible. So there's a lot of technical detail in how you do those pulls. It's not exact. It's not really super complicated code, but it's not trivial either. I mean, because there's an issue of, you want to do what's called a delta pull, where you're just pulling out what are the tuples that have changed recently. Now, this is important, and that is the sync, the data syncs. You build up data syncs in the central process, which will then, once if I pull in, let's say I pull in all the HubSpot data, and then I want to push that out to the production system, I pull it in, and then I basically have these views that are defined that set up pushes into the other tools. So this facilitates syncing across the different best-in-breed tools. Okay, so data sync routines defined via the Lakehouse views push the data syncs between the best-in-breed tools. And again, this is via REST calls. Okay, so what are some of the things that we get out of this? Well, we can query, we can have a whole view over the whole company, because we can see that through what's been built into the Lakehouse, and we can ask questions like for instance, I mean, it's very common, like, well, give me all the deals that are in a certain stage that do not have an accounting record, do not have an accounting project set up for them, because that's like things falling through the cracks. So a lot of times it's just like, okay, by the stage that we're actually doing the work, there better be an accounting project associated with it. If there isn't, could someone fix this? We got to, something's going wrong. So a lot of what businesses do is, a lot of times what their problems are is that they're this is kind of I'm not saying it's a shit show necessarily, but it can be a shit show. That is that the things aren't really working quite right. They don't have things integrated properly, and it's just very interdepartmental. There's a lot of problems. Okay, so what if you have it all in the lake house? You can actually do, and if the lake house is properly reflecting, is in agreement with the tools, then you can kind of see across the whole organization. So that's quite important. And then you can also, of course, join things through. Like, you can ask kind of join questions where, the SaaS tool itself is only covering marketing, and then you have production, and the question might be, and then you have accounting, and you might want to ask a question that kind of spans them all, about like which marketing activities led to the best accounting results. Okay, you can, if you're doing a query over the whole lake house, you have access to all that information. But if you're just trying to kind of do that in one of the SaaS tools, then you don't have access to the full information to kind of like see across the organization like that. Now, a lot of SaaS tools have been trying to kind of push their AI assistants and their AI agents, and they're kind of in a bad position, because that's not really where you want the AI assistants and agents to live. You would rather have them live at the kind of the whole company level. So a lot of SaaS companies are being imperialistic now. They're trying to kind of like, spread out, and kind of like, I'm an accounting program, but I also want to do production. It's like, no. So the best in breed tools approach is, you want to do this in the lake house. So this is the modern data stack. You want to do that in the lake house. All right. Right. Okay. So that's just a bit of that. Right. You can do also reverse ETL. So in other words, what you can do is you can like write down into particularly into custom objects inside of the best in breed tools, or even like custom properties on the objects in the best in breed tools. You can take data that's been derived in the lake house and kind of push that down into those tools again, so that the people using the tool directly can see that. Okay, so it reflects back into the actual tool. So here, I just want to show this right here, just to kind of give, again, to kind of reiterate this. We have N tools, right, that are different departments are using, or different constellations of workers are using. And each of those is reflected in the lake house. It's being pulled in, and then it's also being pushed out to facilitate syncs between data syncs between the tools. And then you also have tables that are actually just lake tables that are inside the lake that people might interact with as well. And then you have, on the top of this, you might have your access into the whole thing. And they may actually be, you might have an MCP over this whole lake house. And of course, you might have MCPs over the individual tools. All right. So that's kind of that. Okay. So let's make some further assumptions here. So this has to do with like this lake house here. The reason why I'm kind of interested in the businesses that are doing, quote, what I would call real stuff, or like, the kind of the businesses that are up to like, I don't know, 200 employees, 500 employees. It all depends on what kind of thing they're doing. Is that, well, what we want is we want scalability. So in the lake house, we'd like to have like maybe up to 500,000 tuples per table. So when you look here and you look at the size of this lake house here, we would, for the architecture here is saying this is one database. This is one database, and it's PostgreSQL. This is a recommendation. This is one single database, and this single database then should be able to be scalable enough to cover the whole business. Okay. Now there are certain businesses that's not true, and a lot of times what the tech industry does, they try to convince businesses that they're going to have serious scalability problems. But the point is, if you're talking about most businesses, they don't have that many tuples. It's like they have, I mean, how many, like, if you take some company that's doing kind of like plumbing jobs, I mean, how many plumbing jobs are they going to have? It's not like going to be 1 billion plumbing jobs. All right. It's not going to be like that. So we're talking real business here. Like, it like doesn't have to have that many records. So the idea then is that if you can kind of keep it, things are scalable until they're not. but most companies can do this by basically running like a single SQL database. Lakehouse can just be a single SQL database on a single EC2 instance, so on AWS or something, or the other cloud providers. So you can just have one. All you have is one. You're just running one virtual server, and that's, what is that like? If it's like a medium, $40-$50 a month. Okay, so that's chicken feeds when in this kind of thing. And that same processor does the pulls and pushes as kind of some kind of core process that's running on that. Doing keeping the pulls a lot of times will happen on a daily basis, like at 1 o'clock in the morning or something. That's when you pull stuff in. You rebuild the lake, the lake house. But then So, and then the pushes as well. So you're doing all that stuff is happening off hours. So it's scalable. So you need to keep it so it's scalable. But most businesses, I would say that most businesses, until you get to super large size businesses, you can run them under one server. Okay. Now extensibility, you need to have the tools need to have custom objects and then this is another thing I just want to say, just because I have experience with clients. You really need to do this like dev and prod. Sorry, I know that people always say, "Oh, you're supposed to test everything out," but no, you need to do dev and prod because it has to be incremental. You need to roll these things out in an incremental way. This actually facilitates that because of the best of breed tool system, but you can't. You got to do dev and prod. I don't see any alternative. Security, you have to deal against data theft, but most of the tools have pretty good like logging into the tools themselves. They take care of that. They're best of breed tools. And they don't typically, you can't get access to credit cards. So the lake really can't, even if it wanted to, it can't pull in credit card data. And, it can pull in like person's names, and that can, so you need to protect the lake from data theft. So generally speaking, what you can do is you can just set up you definitely have to put this under HTTPS, definitely. And then what you can do is you can kind of like, I use the system catchphrase, and the catchphrase basically, there's no database ports that are open to the world. There's a C phrase port, and then C phrase is kind of pretty, catchphrase is pretty restrictive about what it lets you do. So, I mean, it's always a risk though, that people could get the password and stuff like that. But you can also do a lot of things. I'm not sure how well it works really ultimately, but you can put like restrict the ports inside your EC2. So if you know the IPs that are accessing the EC2, you can only have them be the only ones that can get in. I think that works. I'm not really sure. I'm not a security person, but you can. It's a very small surface area. That's the key thing about security, is to keep a very small surface area. And then to make sure that surface area is, And then, of course, you have MFA inside the tools. Denial of service, I don't know. The sabotage, okay, you don't want to let people come in and destroy your data. But the denial of service thing, I don't know. That's like something where you just, it's difficult to kind of protect against denial of service, but you can. It's kind of an orthogonal issue, so you can kind of set the thing up and set that up. But one thing you definitely want to do is set tight scopes on the API access from the lake into the tools. You definitely want to have that. But really, the thing you need to guard against is self-sabotage. You need to make sure your syncs don't like what you don't want to. There's some types of syncs. There's kind of the classes of syncs, and some syncs what they can do is they can say something like, right, if this does not exist in the tool, create this project. That's a dangerous sync, because what might happen is you might actually have gotten like the data got scrubbed or was incomplete or some problem happened. So you don't have any records of any projects in that tool, but then you have a whole bunch of stuff from the lake that could be defined in the tool. And then it just starts spitting in these new inserts into the tool. And then the tool blows up with like just a whole bunch of redundant information. That would be a bad day. So you need to guard against that. It's actually fairly simple to guard against that case with another API check to make sure that this particular record does not already exist in the tool. But it's a possibility. So I think maybe under security, I would call that just like you got to be careful about when you're pushing on your tools. You got to make sure you're not creating duplicates or you're not destroying stuff, etc. Okay. And then I would just basically say that it's just in general, and this is what's also good about like companies that are up to like, medium-sized, mid-market companies. You can probably get, if they go for it, you can probably get executive buy-in. So the worst thing about working with like larger companies potentially is the politics. If they get really political and you don't have kind of buy-in from the leadership to actually do it, because then it's just like, you just get sucked into conflicts. So that's something that there's a benefit to kind of looking at companies that do real stuff, and that are like, I think the owner operator companies are pretty good in this regard, but I don't know, companies can be. So a final question about this whole setup here is, what is the TAM of this? What is the total addressable market? And the answer there is it's quite large. It's probably a good percentage of the businesses around the world. So this is the reason why people are so excited about LLM type stuff, is because it has the potential to impact that broad of population, or yeah. So right. So let's move on now. So now, before we go on here, what I want to do is I want to just introduce some terminology. So this is not necessarily standard terminology, but it's what we're going to go with here, and when we describe stuff, I think it's pretty good. So first of all, there's the notion of what is an automation. Okay, so for instance, these data syncs and like pulling the data in from the different tools. This is the kind of stuff that you should have deterministic code doing. There are a lot of other things in business that should also be automated. In fact, if you can automate it and make it deterministic, and that's good enough, then that's usually the best thing to do, because then you don't introduce this kind of sloppiness that an agent or a call to an LLM might introduce. So that's what an automation is. So we tend to prefer automations, but not everything can be automated, because some things are based on natural language and they're based on kind of judgments that, I mean, you could automate some things, but it becomes very difficult. At one point, you kind of reach this issue of, it's like, well, it's not doing very well. It's missing a lot of cases. So then what we have is we have an assistant. So an assistant is basically, what it does is it builds a prompt, or it's code that builds a prompt, usually by grabbing the information across the lakehouse, or the information from the individual tools, whatever it might be. It brings in, it generates a prompt. It then submits that to an LLM. The LLM then processes the prompt, giving a response, but that response is not acted upon. That response is basically given back to the user as like a digest, like a summary, a suggestion of something, or even a draft document. It's given back. So it's not an agent, because it's not acting. It's just, now sometimes people will say, oh, well, it's an agent because the act is sending the email, but that's kind of pushing it. So it's a little bit vague where the boundary is. But when I say act, what it usually means is making the action. There's a decision kind of around that action. So it's more complicated. We'll see when we get to the examples of agents. And then an agent, of course, is it builds a prompt. It calls an LLM. And then from that, usually via structured responses, it'll go in and it will pull out, it'll extract, so that it's going to have to parse the response that came back from the LLM and extract an action or actions, and then actually perform those actions over the tools, or by making actual calls. So it's going to, this could be like booking a flight. This could be actually going in and doing actual actions. And because of that, what we want to do is we want to start, once we think about actions, that's like a right, that becomes kind of a bit dangerous in a way. So we want to start thinking about transactions. So there's the notion then of an atomic agent, which is transaction-like. So basically, it's going to make one call to the LLM, and the actions that come back, either it's going to fail, it's going to just abort because maybe what comes back from the LLM it can't parse, or some such, or if usually there's only going to be one action, but if there's a sequence of actions, it also applies. They need to all be performed or not at all, right? So it's the notion of all or nothing. Either the transaction commits and goes through, or it aborts. So that's the notion of an atomic agent. Now, multi-agent, so you can have chains of atomic agents that will form kind of some people call this like an orchestration. It's like a set of agents that do a whole bunch of things in sequence. And now we're into an issue where we're basically into a more difficult transaction processing environment. So there's some interesting work recently that it's called Saga LLM. So it has to do with Garcia Molina's concept of sagas, and that is compensation agents or compensating transactions. So if you're really going to do this right, you need to kind of start delving into those kind of issues. There's also the notion of basically extra agents that are doing validation, checking over what the agent is doing, independent agent checking over what the results of the agents were, and then validating that those were correct. And of course, the compensation agents. So this is something I think that's going to be ultimately is going to make it into this kind of agent control or multi-agent control systems. Okay, now an actor in this case here is just a person or an agent. That's all we're talking about. They do acts. Persons do acts, and agents do acts. Assistants don't. Remember that. Automations also do acts, but that's they're automations. Okay, now dispatch. What do we talk about when we talk about dispatch? So that's the question of when and how does the agent get initiated? What is it? So classically, it would be checking the left-hand side of the production rule. So it would be kind of doing a check. It would always be checking. Every time something gets added to the working memory or to the system, it would be to check to see whether or not it was applicable. In practice, I don't think that's really happening quite yet. That may be going to happen in the future. But I think that what the way it generally is being done to kind of keep things controllable is that we have kind of a deterministic dispatch. So like maybe every hour or something, it'll basically check to see, okay, is there any more cases where the agent can apply? So it'll do a deterministic check of the lakehouse or the state of the system. And then, so that's kind of like the left-hand side, but deterministic. And then it will make a call into on a route or something to kind of kick off an agent when that happens. So dispatch is always a question. And then there's also kind of ad hoc dispatch where a person is in the system and they ask for the agent to do something. That's not like an automatic process, but it's kind of a manual kind of ad hoc process where the person asked for that. Okay, good. So now we have some terminology and we can discuss these 9 kind of problems. Now, I'm not sure if these 9 problems are representative or if they cover. I'm trying to make them cover most of the things that I can consider, but I'm definitely open to if somebody hears these 9 and they say, well, actually there's a 10th and an 11th that are kind of distinguished from these that aren't kind of like also variants of these ones. But let me know, because I'd like to have this as kind of complete as possible. So the first kind of, and these problems are going to go from easier to harder. Okay, so generally, okay. So the first one we consider here is this routing, or the customer ticket routing. So the person who's is an office worker, and the problem is how to route customer service tickets to the right representative, to the right person. I guess you could say also agent here. I mean, if there was a special agent, but let's just consider it to be a person that can handle that ticket. So in recitation, we've dealt with this in terms of like routing the for that dealership example. Was it a sales call or is it a call to the garage? Okay. So the benefit is, of course, this saves the customer and the company time. So if there's a quick, there's not too much kind of back and forth. It's nice if it gets routed properly. Now, a baseline approach is kind of what just is being used right now, and then have a person who answers the phone, kind of talk to the person, or you can even have like one of these kind of menu systems, right? That the person can kind of select their way into what department they want to talk to. That's probably the most used. But also, if we think about it, there might be like a vector database approach where it basically takes in whatever it has of the customer ticket, and then it does essentially what we did with the vector database, the recitation problem. It will determine, well, what is what's the closest, and then it will decide that the department based on that, and then a few shot as well. So. And both of these are agents because they're actually doing an action. They're actually saying, okay, they're actually placing the customer in this queue. So it's an action. One thing to say about that, what's the risk is not terribly high, but there is some risk. I mean, people getting misplaced would be kind of irritated, but it wouldn't be anything too serious. Then we have another problem. This is to draft customer correspondence. So this is a case in what we're doing. We have a salesperson, and they basically have a whole bunch of email or a whole bunch of engagements that the customer has been. They have a whole record of where the customer is at and everything, and the customer sends them email, and then maybe what this thing could do is it could speed them up by generating a draft of what their response should be. Okay, the benefit, of course, is just kind of more accurate and quicker, and you can handle more customer calls. The baseline approach is just what happens now, and that is have the salesperson kind of like make their own judgment, and then select things. You could also have a vector database that kind of like pre-populates a templated answer for the salesperson, and you could also use RAG to generate a draft. Okay, so now I think in all these cases, I think you probably want to have this as an assistant. Not as an agent. So in other words, you would like to have this as a draft suggestion. You probably don't want to have an agent that will go and do these things, in the case of generating a draft, and then actually send them out to the customer without human review. So you want the LLM to be an assistant, not an agent, I'm assuming here. Otherwise, it's pretty high risk because you have no idea what you're going to be telling the customer. So that would be, yeah. Okay, now here's a very, very kind of low level type problem, but it's a problem that comes up quite a bit in practice. And it's deduplication. So this has to do with like maybe more the technical or the data staff. So how do we identify records that stand for the same real world object and thus should be merged? So a lot of times what will happen, some of these automatic systems, what they'll do is they'll like create multiple contacts for the same person. Or even you might have multiple deals for the same deal. And then these are kind of both going through the system, and these can lead to 1,001 problems. Because if they don't like do the deduplication, then they're just going to have a pretty flawed understanding of who they're talking to. It leads to a lot of shaky systems to have too many duplicates kind of running around. So so maybe LLMs could help kind of automate the deduplication process. So the baseline is just manual, which is what usually happens. Maybe a vector DBs to notice very, very close. Okay, if there are two contacts and they both have the same email and the same address, but they're just two different, and they have different IDs because they're different records, it's pretty likely that they should be merged. Okay. And you probably want to do this as some kind of assistant as well, because you'll get in a lot of trouble if you merge it and if you just run this on full automatic. But but then the few shot or the vector DB approaches might be applicable here. Okay. So now we're getting into like the fourth problem. So now we're getting into something that's a bit more a little more advanced here. And if you remember, we had the whole lake house, which represented like kind of a duplication of the schema of the tools. So it involves some design. What you might want to do is if you're bringing a new tool in, so let's say you're bringing a new like geolocator tool or something on your vehicles or something, you're going to bring that in. What you might want to do is you might want to say, okay, hey LLM or hey Claude Code, here is my existing lakehouse schema. Here's this new tool with its API. Could you like if I want to like draw from this up into the lakehouse, what is a good table? What are some good tables I can add to my schema, in my lakehouse schema, to facilitate that? Okay, so this is the technical staff again. So how to add new tables or representations of this best in breed tool into the lakehouse. That's the problem. And then the benefit, of course, is a well-defined definition facilitates complete and relevant information being represented in the lakehouse, because you have to kind of build up that lakehouse. Now you could do it completely as a vibe coding exercise. Like you could say like, oh, here are the tools I have. Like if you were starting fresh, here are the best in breed tools I have. And this is kind of what I want to do roughly. Could you assert a schema? Could you build a schema for me for my lakehouse? And then Claude Code or something like that would actually just go ahead and do that. It would build that schema And then you would, if again, like if you recall earlier when we talked about this kind of vibe coding versus code assist, remember that it's kind of like a pretty common use case goes like this. You use the tool to vibe code it in the beginning, and then you take possession of it and you go in and you start like simplifying it and kind of getting to know it, what came out of that. But you still could get some pretty considerable speed ups by doing that. If you want to kind of automate, semi-automate the building of the lake house. If you want to do complete vibe coding of it, so that is where I'm a bit more skeptical that, I mean, you could maybe get something to kind of halfway work, but if you want to always stay away from the codes, keeping that I mean, the good thing, like vibe coding can like speed you up in the beginning. It can also be like, once you have everything really stabilized, you can take another kind of leap with either vibe coding or code assist. But generally speaking, you want to have control over that, because I mean, this is really kind of critical representations and processes are in there. So I don't think you want to just stay detached away from it. I mean, maybe there are really simple businesses where you can do that, but I think in more complicated businesses, you really want to keep control. But anyways, the baseline is just to do it the old-fashioned way. Then you're going to do it as an assistant, or as, with Claude Chat or Claude Code. You would want to kind of build that out. Okay, I think there's a good reason to believe that you could get a good speed up. But what we would want to do here is we would want to run some controlled experiments to see how well this actually performs. Honestly, I find that a lot of times what those tools do, I always have to tell them, for instance, that they always try to point me towards something like Vercel, or they try to point me toward SQL Alchemy. And if anybody knows anything about me, I am not a fan of ORMs. So I always have to kind of have my prompt say, no ORMs, no ORMs, object relational mappers. That is not what I want to be using. But it's kind of flat, kind of like ER, entity relationship diagram based schemas. That's I think the best bet. Right. Okay. So along with this, then we also have the actual pull and push code that's around that schema, that's going into the APIs and doing the pulling, and then the opposite side of doing the pushing. Now, I've had actually some pretty good luck with doing this, some good experiences with this, because you set the schema. You still have to sometimes kind of like tell the thing, okay, you want it to like generate the kind of code you want to have. So I find actually that what I do is sometimes a very, very common use case I have with this is I'll build like a pull code, and then APIs. You know how it is with REST APIs. I mean, they're very finicky. And so sometimes what I'll do is I'll just do a really rapid attempt to kind of like, okay, this kind of maybe works. I look at the documentation. I just do a really fast implementation of it, and then it doesn't work, of course, because I just did it too quickly. I'll paste that into Claude Code and I'll say, can you fix this, please? And it's remarkable because sometimes it'll actually see kind of what the problem is and it will explain that and it will fix it. And I get really, I swear I get speed ups with that. But these are kind of like the pull and the push code. So it's, again, technical staff writing Python code that will access a tool. So one of these best in breed tools, it'll access its API and then pull the data up into the lakehouse. And of course, it's not, I mean, writing pull code is not very fun in general. But again, though, it's pretty important that it gets it right. So you got to do a lot of validation of it. And that's even more important if you're going to do push code. Push code that is where you're making calls on the API to make changes in the underlying tools. That's a problem. But I think these are both pretty good if you've kind of settled on the lakehouse architecture. So you're not letting the LLM decide giant architectural issues. It's very much kind of in the small of how it's actually going to do the actual pulling and pushing. So I think in that regard, it kind of works well. Okay, here's another problem, which I hopefully will have enough time to kind of get you guys to play with for recitation. It has to do with schedule building. So this is kind of like an operations staff would have this. So that is, how do we automatically assign crews to jobs in real time? So let's imagine a company where we have a whole bunch of customers out there in the field who need to have, and they've called in and they've said stuff like roughly when they want to. I mean, and they might even been using natural language as kind of an important aspect of this. They've called in and they've said kind of when the crew can come out and do its work. Um, and then the issue is this: is that we have a bunch of crews, and the crews, of course, there's like bringing the crew out to the site is going to cost time and money. Therefore, you got to pay people when they're in the truck or going out. And then, of course, doing the job, they're going to be paid because it's the amount of time it takes to do the work. And there's always these things that are kind of happening, these events happening that you don't have control over. So if you're like had a lawnmower business, like lawn services business, raining out, so it's too much rain, we have to cancel that. So there's a lot of dynamism in the scheduling. Okay. So what I'm going to hopefully do for recitation is set up a system that it kind of is behind a veil and is doing a deterministic model of generating these jobs, and then there are the crews, and there's the schedule. And what your agent is supposed to do, they're supposed to say, okay, kind of in a piecemeal way, given this schedule, given these current assignments with the crews and all this, give me the next assign this job to a crew at a time. Okay, so let's kind of fill in the schedule. And then what can happen then is that since that can be deterministically scored. So in other words, there's kind of, I can look at that and I can see kind of what's going on. I can see, oh, we missed that job, missed it, whatever, it's like, I can basically, for every job we get paid, but for every job we're also paying the crew, and we're paying to get the crew out to the site, both in terms of the number, how long it takes to, they basically just the routing. And then, so the question, of course, is that if you have that kind of deterministic way that you can score how well an agent is doing, then you're really in good shape to kind of set up an agent that does this kind of scheduling task and maybe get some really kind of interesting behaviors. Okay, so I'm not sure if we'll get a chance to do that in recitation, but that would be cool if we do get a chance to do that, because it would be like really kind of closing the loop on an agent and evaluating how well it's doing scheduling. Okay, and the baseline would be just doing a human doing the manual. There might also be another baseline, not so much a baseline, but just running an old-fashioned algorithm. Like you're going to just kind of cracking the algorithms book and then trying to kind of code this up as a deterministic algorithm or an approximation algorithm or something, and seeing if that's just kind of, that will take you so far. But the thing is that if you wind up starting to have kind of like natural language descriptions of when the customer would accept what are good times. Once you start adding in kind of more and more of the kind of like extraneous details of the world and all the things that we kind of use as common sense, a scheduler could use as common sense, then maybe once you model at that level, then you will start the kind of real pure algorithmic approaches will start breaking down, and then an LLM agent would actually do better. So it's a question. It's an empirical question. We would like to kind of get to the bottom of that. So I mean, these are, remember, all these examples I'm giving here, these are just really kind of, I'm not sure if there's like definitive answers yet about these. So we're trying to kind of muddle our way through and figure this out. Okay, now related to this is something like doing something even bigger, and that is like kind of doing like an estimation draft, generating a draft estimation of something. Okay, so the estimator, so this is a very common role in businesses, is that, so the customer comes, they say, well, yeah, I know you guys can do this kind of service or whatever. Maybe it's like a roof job, or it's a job of like, it could be like really almost everywhere where there's complex business going on. You have like some idea of like the customer comes to you, they talk a bunch, you share information, then you construct an estimate and you give that to the customer and say, here's the estimate. Do you want to buy or not? That's very, very common. So the issue is that to what extent can we kind of get LLMs to help draft those out? Because those require a lot of work, but they're very detail oriented. So that's why it's more difficult. Right. And then of course, and another thing just to remember is that when you do that, if you're a business and you do an estimation, if you have whole bunch of change orders like crossed overruns or something, it's going to hurt your reputation. So you would like to get the estimation right the first time. So that's something to consider. Okay, baseline is just the way it's being done. Right. So you can bring in maybe lots of kind of RAG based, so agent. Basically, I think an agent based approach might be something to kind of to look at and to evaluate to see kind of how well it does. It's not so much it's an assistant actually in this case. I shouldn't say agent. It's an assistant because it's a virtual certainty, except it's in extremely simple businesses. It's a virtual certainty that you're going to want to have this in a draft status and then have a human being look it over. I mean, this is, otherwise, what if the thing, you could really ruin your business, right? If you're sending out estimations that are just really lowball, and then the customers say, oh, yeah, sure, I'll take that. You sign your name to it, right? So then again, there's most likely going to be some kind of cost overrun if it's really, it's a bad business to be sending out estimates that are too low. You don't want to do that. Okay. All right. Now let's go to the eighth and ninth, and this one there will be an example of this in recitation. This is an idea of a tutorial system. So in business, though, you might have a new employee, and the question is that how do we get them up to speed? How do we teach them, some of the details of the industry and like the structure of the operations of the firm, and the details of their job duty, like training, right? We want to onboard people, so it's a teaching task, and right. I mean, an efficient, effective, pleasant onboarding process leads to quicker time to profit and greater employee satisfaction. So people are going to appreciate it if, I don't know, for a lot of jobs I took when I was younger, it was more like they just kind of threw you in the middle and it was kind of sink or swim. And usually you ask a lot of questions to the people that were there already, and they are more or less cooperative in answering, but it's like a sink or swim kind of thing. And sometimes, having a nice onboarding process would actually be, there are benefits to that. There's definitely benefits to getting people quicker up to speed. Right. Okay. Yeah. So the baseline waves that you basically say, what I was talking about is you just toss people in stuff and they have to kind of figure it out. But here, read this, kind of thing. But potentially like some kind of advanced RAG over a corporate knowledge document base might be something. And I think that what's interesting here is this idea of a COALA agent doing active teaching. And when I talk about active teaching, what I'm talking about, so this is really beyond the state of the art at this point, but what one would talk about is like, one would say, like when you're interacting with a student, the first thing is you're saying stuff to them, and then that's having a causal impact on them. So then they're doing something, and you're observing that, and you're thinking, okay. So one of the first questions, of course, if you're trying to teach somebody something, is that do they even want to learn this, or are they just kind of are they eager to learn this, or are they just kind of like a little bit too cool for school kind of attitude, and they just don't? They would really rather not be there, because in that second case, then you have to kind of maybe adopt more coercive teaching methods, like lots of quizzing and lots of And the other one, you can have a more Socratic. More interesting kind of deeper discussion of things. But the point is that setting up an LLM just to kind of have like a checklist of that's not what I'm talking about here. I'm talking about really like trying to kind of form a causal model of how the person is do they really understand what I just said? Okay, I'm going to say this now again to try to verify they understood that. It's much more intricate when we talk about kind of at the level of kind of human conversation. And also the thing is the timing is much more natural as well. And there's the whole kind of right. Like the extent to which like there's silence in the cues you can get from like a silent patch. Thinking Machines, by the way, the company Thinking Machines is looking at running LLMs and trying to kind of get down to that kind of continuous time for chat, trying to get down to continuous time interaction. So that's something. But still, is there a way that we can have a much more an active teacher? Or just in general, how do we build teaching systems? Because the teaching system, it's a little bit of a reversal of the chat system, because in this case, it's the goal of the agent is to impart knowledge to the recipient. So the agent is really trying to figure out, have I given all the knowledge that I have that I'm supposed to the recipient. or in this case, the new employee. So I think it's an interesting question, and you'll see in recitation. I've run that recitation problem before, and I got some pretty interesting kind of approaches to this problem. But still, everything kind of falls a little short. But this is something that we'll see if we can develop. I mean, but they're still useful, it seems. Okay, the final one is like just like the kind of maybe the executive's dream. Yeah, I mean, well, there's in the next lecture we're going to be talking about some of the we're going to really look at the kind of criticism, so the societal criticism of the whole LLM. So if people are wondering kind of from a level of kind of like society and all that, there's lots of people who have things to say about this idea here. But the idea here is that we have a chat. We basically have a co-work. So co-working is like doing, right? So I think I already said that before. It's like chat is like reasoning or discovering. Co-work is like doing, and then Claude code or coding is building. But in this case here, what we're talking about is we're talking about a co-work type situation where the executive wants to kind of, they have MCPs hooked up to the lakehouse, to all the tools, to the documents they have that govern their organization. And to maybe the Slack channel because they want to talk. So there's that's another tool, Slack. So they want to sit there and they want to basically just have a chat with the whole company, like what's going on, ask lots of probing questions. This is of course translating down into like SQL type questions over the lake house. It's turning into different. It's basically it's accessing all the MCPs for all the components of the system, and then moreover. The executive can also through that channel as they discover stuff and they get reports and they're kind of like just looking into the business completely. They can start actually issuing orders through the system as well. So it's kind of like the one interface, the one controller and observer of the whole organization. Okay, so that's kind of what the ninth. It's pretty vague. It's pretty big, but the way you get a first cut at this is you just set up a whole bunch of MCPs, and then you bring in something like Claude Desktop or CoWork, and have it just kind of go and start chatting and see what you can do. So in that, what's happening then is the harness around Opus or the Claude harness. It's going to be basically, if it has failures, and that's going to rephrase questions. It's going to be doing. It's going to chart its way through, and then maybe give up certain times. But it's going to be this kind of right. That's probably the state of the art. That's probably state of the art. That's probably one of the most advanced use cases that people are currently trying. It's still hard to say really how well that's going to perform, but I think it's a big problem. So it's very ambitious. So yeah. So anyways, that's it. Those are the 9 ones I came up with. And again, please let me know if you have additional ones that you say that I haven't touched on. Actually, it kind of occurs to me there was one that I didn't touch on, and that is like the pure case of like customer self-service through a chat. So the customer it's kind of similar to this one a little bit in a way, but it kind of has to be more guardrail because you can't let them just do anything. But so you have to kind of guardrail it to what they can do. But yeah, maybe something like that, or like them doing like calls to try to resolve their problems via a chat. People don't like that in general. People are starting to complain about that, but it's still maybe that would be like problem 10 or something, or problem 7, and then the other ones would move up because I think problem 9 is the hardest one. Right. Okay. Great. All right, guys. I'll try to get recitation out. Today I hope, but at least partially today, and then try to finish it up. I really would like to get that scheduling thing built. I just hope it goes well. We'll see. Okay. Thanks.